Hello and welcome to NARC Live on Wednesday the 6th of August 2025. Coming to you live from Norfolk on the east coast of England with Tammy N0AX, and I'm getting a worried look from her.
Hello? I don't think your microphone's working.
I can have some...
Or is it my microphone? Oh, somebody's microphone is...
Might be this. Well,
I did ask you if you turned your microphone on.
I did, I had. Anyway.
Should we start again?
Yeah, let's start again.
Welcome to NARC Live.
Edit. It's a good job it's not live. Oh, hello, good evening and welcome to NARC Live on Wednesday the 6th of August 2025. Coming to you live from Norfolk on the east coast of England with Tammy N0AX.
Hello.
And me, David G7URP. Great to see you again. On tonight's show, we find out about the end-fed half-wave antenna with Ward N0AX. Check this out. See what I did there?
Yeah.
And we find out what on earth this is. But first, I'm sorry to start with the very sad news that Steve G7VRK is silent key. He passed away suddenly last Wednesday after a very short illness. Steve was not on the radio much in recent years, but he still retained his antenna and tower and had played major roles in both our club, Norfolk Amateur Radio Club, and the N0AX Club over the years. I've already sent his wife Christine a sympathy card from our club, and our thoughts and prayers are with all of his family and friends. Steve G7VRK, sadly now silent key. Now, if you've checked your mail inbox today, hopefully you may have just received, in fact, an email newsletter, a NARC extra as I call it when I wrote that earlier. And on there are quite a few extra summer events that we hadn't specified dates for yet, just to sort of complete our summer calendar. So Tammy's just made up a slide for us, so let's have a look at those items and go through them. One major event coming up, which has been organised actually for a little while, and Malcolm G3PDH along with Kevin M0UJD is organising this year's GB0HL, Lighthouses on the Air, Lighthouses and Lightships actually on the Air. It's an international event, International Lighthouses and Lightships on the Air, and for many, many years our club has activated Haysborough Lighthouse for this special event station. Now, we'll be there both on Saturday the 16th and Sunday the 17th of August. However, it's open to the public as one of their open days on Sunday the 17th of August. But on Saturday the 16th, we've actually got the place to ourselves, as they say. So, a lot more details are in the newsletter and in an article in their own right. Again, on the latest newsletter went out today. It's also on the front page, the homepage of the website as well. And on there, you can click and choose your own operating slot, because obviously we need lots of people to operate on those 2 days. It's only really practical to operate one station because the acoustics in a lighthouse, as you may know, are pretty awful really. It sounds like a bathroom times 10, you know, in terms of echoes and things like that. So we think on the Saturday the 16th you can work SSB as well as CW, but a headset is almost essential because otherwise the reverberating around is impossible. The trouble on the Sunday the 17th of August working on SSB is there are so many people about. We don't want to put anybody off if you want to try and work SSB, i.e. voice, on the Sunday, but it's quite a challenge with everybody around, both to hear who you're speaking to and also for others to hear you, because there can be quite a lot of people and there's quite a lot of noise about. So Saturday the 16th it's all modes and all, but probably the Sunday the 17th of August mainly CW unless you want to give it a try on SSB. But we do need you to take part. It's a wonderful event, and we've been doing this, as I say, for many, many years, and Haysborough Lighthouse is unique in being the only privately owned lighthouse run by a trust in the whole of the country still. So if you want more details, please go have a look on the website or on the newsletter and click on the link to have a look at the roster, and you can get in early and get your chosen time and day on there. Thanks very much to Malcolm for organising this, and Kevin is going to be helping on the weekend as well. Now, the next item you can see on there is not actually officially, I suppose, really you could say a club event, but Paul G3SCM was a club member, excuse me, and as you may know, about a year ago, it was last spring really, we ran a clearance sale basically. He was downsizing his shack, his considerable collection of radios and equipment, which he's collected over his whole lifetime of being in this hobby. Sadly, of course, we lost Paul early this year. So now it comes to me to arrange the sale of all the rest of the equipment. And I have to say, actually, kind of really the best equipment was left till last, because a lot of the good things that he had, the best things, he kept because he wanted to keep operating as long as he could. But we're selling all of those things now, and we're going to have a day sale, again, an open day, at his home with his wife Rita's consent and blessing on Saturday the 30th of August. Now all this is at the moment is just getting you to put that in your diary if you're interested in some of the equipment. I realise you'll want to see a list of that, and I'm busy typing it all up, and then I'll be publishing that soon along with some prices as well. Now if you can't make the day but you're prepared to pay the price, which all going to be realistic prices, then you will be able to buy them or reserve them before the day. But lots of people I think are going to wait and see the things on the day. There's quite a few other things as well which I can't possibly collate and list. He had a really big collection of cable, not just any old cable, but everything's on nice reels and everything, because Paul, I think, a bit like myself, I'm the same. If you want some cable, if you could afford it, he bought a reel of it. And so there's a wonderful selection of cables. So if you want any cables for your stock or anything, it'd be a great opportunity. And lots of components as well. He was a budding constructor. And again, I can't possibly list little drawers of components, but they've all got to go now. So there's a lot to do, and we feel that an open day is going to be the best way to do it. So please put that date in your diary if you're interested. And watch out on the newsletter for a complete list of the equipment, the main equipment that is, nearer the time. Now, I've mentioned this for many weeks now, but we've got a Hamfest coach trip. It's on Friday the 5th of September. One thing that's changed today, which is a wonderful thing to match, is that we've today sold 26 seats. Now, I actually started by organising a 26-seater. And as of today, lunchtime, we had someone else book a seat. So we've now sold exactly 26 seats. Now, of course, I don't want to hold anybody back, and it might be nice even to have a slightly bigger coach. But I do need to tell them and say I want to change my booking from a 26-seater to a 52-seater, which will give us lots more space on board. So if you want, if you do want to go on this trip, it's definitely going ahead. Please book as soon as possible. As soon as I get another booking, I'm going to be reserving that bigger coach. That means, of course, you can fit lots more stuff in there. Some people may be like me, and I've got a line manager going with them to the Hamfest, just to keep an eye on what they buy, because I don't need anything, do I, Tammy?
No.
Right. But also there will be a lot of room to bring stuff back, especially things like aerials and things. There really is no limit in a coach fitting stuff underneath.
Maybe just not a trailer tower or something.
Well, not a trailer tower, maybe, no. One of those big masts. And also, by the way, if you do have a mobility scooter and you want to take that, that's again no problem at all. Most of those, as long as it collapses down, the front bit collapses down, then you can take that too. Okay, so that's really good news. I'm glad it's now we won't also be subsidising, which is wonderful. Now, another date, you'll know that in July we were going to have a radio by the seaside, but we had to postpone that because the weather was terrible. The forecast was thunder, lightning, and goodness knows what. And even if I'd ran it, not many people would have gone, I think. So it was postponed, and because the car park and everything is so busy this time, and this time of this month, because of the schools' holidays and everything, they don't give us an area. They can't give us an area of our own. However, they can as soon as the school's gone back. So I've chosen Sunday, the 7th of September, which is just after the schools go back. When they're happy, and I've corresponded with them, they're going to give us our usual area there, all to ourselves. So you can put up aerials and do all sorts of things. And that's, again, another date for your diary, just over a month away, Sunday, the 7th of September. And then finally, a date that has been in our diary for some time, but it's confirmed by the Foxes. We've got a friendly, fun fox hunt, that should really say, I guess. This is one where maybe the Foxes are going to play around with the rules a bit. It's purely for fun. It will probably be on Sunday morning up to lunchtime. And who knows, we might even end up somewhere where we can have a nice bit of Sunday lunch somewhere. But again, if you're interested in direction finding competitions, i.e. fox hunts, then please put that date in your diary.
Are we there?
We're there. Thank you, Tammy. Now, a couple of other things to say to you. We have been asked to support another DXpedition to Beauvais in 2026, or Team 3Y0K. Now, some of you may remember that some years ago we supported their earlier attempt, but there were quite a few problems getting there. And although I think they did manage to get a few signals off there, they certainly didn't deploy onto the island and do everything they intended to do. Well, they say that they are much better organised and prepared. Now, they've tried it once and failed. And this is, of course, in the top 10 wanted lists for DXpeditions. Now, they've approached our club and said, could we support them again? And we're minded to do so. But we really do need to ask you, the members. We don't actually democratically have to ask you for anything under £500, and I'm sure that we won't be giving them that much or more than that. But the committee had a meeting. We thought it was right to put it to the membership. So we are minded to support the event. If you have any feelings either way, though, for us to support this, we are a large club, I think, in the scale of things, and financially we can afford it. But if you've got any feelings pro or against, please do drop me an email to the usual address, and we'll make sure that we take all those things into account before we make the final decision. Years gone back, it would be fair to say that this sort of decision we do at the club, really, and have a show of hands. But although we do get a strong number of people at the club now, 30 to 40 typically in a week, it's nothing like not even half of our membership, which is approaching 250 now. So really, the only ways of communicating this sort of thing up is to do it this way, either on NARC Live or on a newsletter. So if you have any feelings pro or against us supporting Team 3Y0K for Beauvais Island next year, then please drop us a line to this address, radio@dcpmicro.com. Now, many of you are involved in scouting, and you'll know that every year on the third weekend of October there's an event called Jamboree on the Air, or JOTA, and radio amateurs traditionally have been involved in helping scouts both get on the air and talk to other scout groups and others individuals, but also to show them some of the wonders of our hobby. Now, I know many of you, as I said, are involved with that already, but I've been approached by another scout group. This one is a Sea Scout group, and they are in Dickleborough, and they've approached me to say, is there anybody that could help them, or any 2 or 3 amateurs maybe who could help them put on a station. I know already that the people who are usually involved with scouts already be doing that in their usual scout groups, and of course we shouldn't take them away from those. But this is really an appeal to anybody, any club member who would like to put on a station, help them put on a station. The club, I'm sure, will offer support. We've probably got equipment and things we can lend you as well, but we do need people to do it. So the actual dates are the 17th to the 19th. That's the full 3 days, as it were, of October. If you would like to help that scout group in the south of our county put on a station, then please do get in touch with me to the usual address. Again, it's radio@dcpmicro.com, usual address at the bottom of your screen. And if we can get 2 or 3 people together, then we'll try and make sure that event happens. As I said, the club can help with various bits of equipment as well. That's almost all, well, it is all for the club news. Now on to members news. And as you may have seen at the beginning of the programme, Donard, N0AX, sent us this picture he thought would amuse many. Now, I'm not good enough to know what types of valves they are. I guess the king and the queen are the ones in the middle. I know basic rules of chess. So they're the ones in the middle on the right and the left-hand side. You've got the pawns in the front, which I guess are going to be...
I'm not sure that the valves will be called the king and queen, though.
Well, no, they might be, though,
They are the
Tammy.
king and queen, obviously, because it's a chess set, but I don't think you get a king valve or a queen valve.
No, you don't. Well, no, but you have triodes and pentodes and things like that, don't you? Yeah,
I think
PA valves.
I think you're reading a bit too much into it.
Am I?
Yeah.
I think it's great anyway. A lovely picture. Thank you very much, Donard, for sending that in. We won't have a long debate
Big
about
old
it.
set, isn't it?
It is. The pawns at the front, look, are just... I know you said prawns. Then the pawns at the front are obviously little valves, maybe diodes or something like that. Anyway, thank you very much, Donard, for sending that to us. I'm probably reading far too much into that.
You are.
So, Tammy, over to you with Little People.
Well, actually, just before Little People this week, you nearly got replaced earlier.
Yes, I did come round. Believe it or not, we rehearsed this show, and about an hour ago or something like that, I came in here and my seat was not clear. In fact, it had our cat. I know you said our dog. Our cat Denver was sitting on it, looking not at all worried. There's my shirt on the back, ready for me to wear. He sat there very peacefully.
He did, and then I sort of told him it was really time to go. And this is the funny part, really, because as he jumped onto the floor, he mic'd himself up because he jumped through the wire on your microphone, and he was sat there with the microphone on his back.
Yeah, so he really did become nearly the presenter.
He did, yeah.
You could have locked the door.
I nearly pulled him back then.
Yeah. Because we leave the microphone on top and he just somehow got tangled. And that's not a put on.
No, he literally jumped through your wire and got tangled in it.
Luckily, Tammy had her phone nearby and managed to get a picture of this.
And then I did untangle him.
So if one week I can't make it, you're happy to do that with Denver, eh?
Yeah, we did have a trial with Bugs Bunny once, didn't we? But I think
over the difficult times.
Denver dog might be.
That was that a Fox hunt, or was it when we did the one at Christmas with the repair shop?
It was Christmas Bugs Bunny.
Yeah, and I look back and there wasn't.
He's got his bell and his carrot.
Do you remember those days? Years and years ago now. Seems so long ago. Anyway, do keep. Oh, we haven't done little people yet. I cued you, and you told me about something else that I didn't realise you were going to show that. But anyway.
Are you having a clear out at the moment?
Not right now.
Well, do you know what to do with all your old cassette tapes?
That's embarrassing, wasn't it? No, I don't. Can you hear a blush? Because there is one. I think we should show your picture, Tammy. Come on, press that button and show everybody your face.
She's crying. Right, this is what you need to do with all your cassette tapes.
Yeah. Is this an airport?
This is like a ticket booth.
Right. I hope they're laughing along at home. Okay. Thank you very much for that. Miniature-calendar.com. We try and keep it clean every week. We have for 5 years now, and we don't intend to spoil it now. Miniature-calendar.com. We put a brand new picture on every day, and Tammy picks one for us. Thanks, Tammy. Come on, back to you. We want to see your face.
I think we better get you.
No, don't you do that. Come on. Everybody wants to see you.
I'm just laughing.
So anyway, do keep in touch with what you've been doing. Come on, you're going to tell me which camera to look at, that one. Yep. And do keep in touch with what you're doing. Look at the blush.
Yeah, I've got the same colour as my
red chops.
My red chops.
Do keep in touch with what you're doing. Send us your news, just like Donald sent us that picture of that cool chess set. Anything like that at all, just to keep us engaged and fun. Just send them to the usual address, radio@dcpmicro.com. Anything at all for the show. We'll be happy to share that with you. It's given us a good laugh, that, hasn't it? Right. Yeah. Now let's go on to our competition, because we're very shortly going to meet our guest for this evening. And let's see. And when I asked you 2 weeks ago, what on earth is this? Now, I thought this was really difficult. I wouldn't have got it, specifically what it was. But let's see what people said. Tammy.
Oh, hang on.
Oh, do you want me to start? Okay. So Merv, MI0, TMW, was first off the bell and said, possibly a fire door release solenoid. Yeah, I can get that.
Mark M0MEA is a bimetallic strip.
Bob G6PWS says it looks like a relay cutout unit. Not sure what for, possibly for an appliance or testing unit. Mike
GAEEY, I think this is an overload cutout from an Avo 8 MK5 meter, Mark 5 that is, isn't it? And you may well have a bent pointer in the meter movement as well. The last time I saw one of these was when I was working at Marconi Radar on Rivenhall Airfield, when an Avo 8 fell 30 feet onto the concrete runway, and there were no pieces left larger than this one. Ouch, no, I didn't drop it.
Good. I think you'd been in trouble and lost your job, Mike. Bob GSTU says, my guess is it a thermostatic control. Yeah, totally get that.
Colin M0GMK, this week's What on Earth takes me back a few years from when one of my work colleagues was a wizard at repairing analog meters. I think it's a cutout trip from an Avo 8.
And the answer is...
Dun, dun, dun. It is the thermal cutout
Bang
from
on.
an AVO 8 meter.
Absolutely. So special well done there to Mike and to Colin, because they got it exactly right. A lot of others were very close. They were saying a relay cutout or bimetallic strip, which are all the ways, of course, these work. When they overheat, they break the connection. So they get half a point as well.
Yeah.
But anyway, good. Well done to all of you for entering. I think that's really good. I didn't have a look at anybody at home.
No, everybody's just commenting on the cat.
Oh, are they really? Oh, yes, they are, aren't they? We ought to refer to a few of those. We'll do that in a minute when we just get this competition done. Okay, so thanks very much for entering. Thanks to Tom, GXQD, who sent us to... I must admit, when Tom sent that to me, I thought, nobody's going to get this. Because it was so obscure. I could probably work out that it was a cutout, but I didn't know what it was from. So well done. Thank you, Tom. So let's find out now for the answer for the competition, because, by the way, we're meeting again next week, not in 2 weeks' time. So you've got just under a week to let us know what on earth is this? Or what is it for, if you don't know the name of it. It's got a very specific use, or actually a couple of uses. That's all I can tell you, really. I don't know if that's 3D printed. Maybe it is.
Yeah, it's just a piece of plastic.
But it is really good. It's ingenious, and I'm not allowed to say any more, or my line manager will tell me off.
Yeah.
So answers to us by 3 o'clock next Wednesday at the latest, please. To radio@dcpmicro.com. Have you ever used one of these? Do you know what it's for? You don't have to know what the proper name is, just to tell us what it does will get you the point that you need. Radio@dcpmicro.com next Wednesday at 3 o'clock, please, because we'll be seeing you again next Wednesday evening. So thanks as well to many of you came up, rose to the challenge of sending us new pictures of new what on earth. So we're going to got enough to keep us going for another few more months, but that doesn't stop any of you. If you've come across something you think, I bet nobody knows what this does, they're quite clever lot. Watch this show. Don't forget to drop them to us in the usual email address, the pictures of it, and then we'll include those in future competitions on NARC Live. So before we meet tonight's guest, coming up in a moment, just time to let you know what's happening this week at NARC. On Sunday, of course, we've got the GB2RS news on GB3NB. Next Wednesday, the July the 13th, excuse me, it's a double week of NARC Live, as I said, because we've got Bill W5SJ, who's going to be talking about being an accidental contester. We're back to CNS, by the way, the week after that on Wednesday the 20th. Wednesday the 20th of August. And as I said, please do keep in touch with your news and everything. And of course, these, if you want to send a birthday card or greetings card, or just want to cheer someone up, we're always happy to send one of these cards out. Just drop a line to me, to this address, please, with their name and address. We'll add your name to ours and send them off to them. Now, tonight's programme, tonight's presentation, is all about an antenna that I must admit, personally, I've got a great admiration for. Because whilst many of you will have big, massive antennas on towers and rotators and everything else, a lot of people have to make do with something a bit simpler. And wire antennas, of course, are great. And personally, I found the one that's really, really good is an end-fed half wave, which Steve G0KY recommended to me a few years ago, and I've never looked back because it stays up in all weathers and it's a brilliant bit of technology. But we need to find out more about it. So tonight we've got Ward N0AX from the States going to come and tell us. And welcome to you again, Ward.
Glad to have been invited. Thank you very much, and looking forward to the presentation.
Yeah, we're really looking forward to hearing from you. So as usual for everyone at home now, if you have any questions or comments for Ward at any time during the presentation, just drop them onto Facebook or BATC and we'll be sure to read them to Ward at the end. But now, over to you, Ward.
Okay, thanks. And very glad to be back with the club again. Wonderful visit last time, an e-visit, an online visit, and got some good comments. So I'm happy to be back and to talk about an antenna this time. So it's a fun topic, and the end-fed half wave is such a popular antenna right now. There's a lot of discussion about it, and so I thought I'd put together this talk. So let's jump right in. Here we go. This talk is going to talk about the end-fed half wave family tree, where it comes from, and how did we arrive at this particular antenna. It's very similar to some other antennas, and maybe surprisingly so. And then in feeding, there's a lot of myth versus reality about exciting an antenna at the end instead of most of the antennas that we use, which are excited in the middle or somewhere along them. What's the difference? Why is infed such a big deal, and why does it work? Then we're going to talk about impedance transformers, which are really the key to the infed half wave and really make the design functional and efficient. And then we'll talk a bit about counterpoises, poise and counterpoise, I guess, which is also another topic that gets considerable discussion and lots of different definitions of this. It's a very old term, so we'll talk about that since it's a part of the infed half wave. And then putting the infed half wave to work. All this theory and explanation is very nice, but how do you actually use one to the best of its abilities for an effective and efficient antenna? And you can make your own. It's fairly straightforward, and if you're willing to wind an impedance transformer and drill a couple of holes in a box and measure some wire, well, yeah, you can make your own. So let's get started. Let's go way back in the family tree to the center-fed half-wave dipole, and it was the first antenna ever used. Here, Professor Dr. Heinrich Hertz did experiments in 1885 to 1885 to 1889 to see if he could demonstrate the existence of electromagnetic waves that were predicted by James Clerk Maxwell in 1865. When Maxwell's laws were originally formulated, the mathematicians and the physicists looked at that and said, there must be a wave. This looks like an equation for a wave. So they didn't really have any test instruments. The electronics industry was somewhat in the future, and so they didn't really know how to generate them or detect them. And that fell to Dr. Hertz, and you can see a picture there of his experimental apparatus. He has a metal ball on each end of a wire that's about 2 meters long. So the first electromagnetic waves were really around 100 megahertz. The balls at the end of the wires make them look a lot electrically longer. And there's a tiny little spark gap in the middle. That was his receiver. So that is the very first antenna right there. You can read all about it on Wikipedia. And after he had demonstrated that these waves existed by exciting antennas and using reflectors and focusing apparatus, and somebody said, well, you've just discovered these electromagnetic waves. What are they good for? And he said, well, nothing, I guess. So we know things are a bit different. But anyway, that's where the center-fed dipole, half-wave dipole, got its start. And still today, after 130 years, dipoles are still the best bang for the buck or the pound or the euro in ham radio. They're very simple antennas. They're very efficient. They're tolerant of their surroundings and inexpensive, easy to put up for the most part, and they radiate and receive very well. So if you're, quote, stuck with just a dipole, you're doing pretty well. You're in good company. The center-fed dipole, the word dipole comes from the prefix di, which means two, and the pole part means not the poles that you hold it up with, but two voltage polarities, one positive and one negative, and that's what causes the electrons in the wire to move back and forth. And so when the voltage is positive here and negative over there, then the electrons move in one direction and then they reverse in the next half cycle. And so they move in the other direction and it goes back and forth. And what you wind up with is accelerating electrons in a straight wire And that is the most effective way to make an electromagnetic wave, as it turns out. When a dipole is resonant, current and voltage, current represented by I and voltage by V, are in phase everywhere along the antenna, along a dipole. And that's what resonance means. It doesn't have anything to do with feed point impedance or radiation resistance or anything like that. It's the condition in which current and voltage are in phase. And you can see a drawing of that at the bottom. The dotted line, let me see, bring up my little cursor here. The dotted line represents voltage, and the solid line represents current, and the size of the arrows represent the amount of each. Feed point is at the middle, and as you can see, the voltage is high at the ends, as anyone who's touched a dipole while someone is transmitting at the end knows very well. And so it goes from a high voltage here down to a minimum at the feed point, and then sorry about that, and then it reverses polarity and becomes a high voltage at the other end. The current is 0 at the end because there's no place for it to go, so it stops. And so you have 0 current at the end, maximum current in the middle, and minimum current on the other end. The current does not change directions along the half-wave antenna. It stays flowing in the same direction the entire distance, and that is a half wavelength. The actual movement of electrons is very short. An electron might move a few millimeters during an RF cycle, but the entire cloud of electrons in the antenna is moving back and forth, and that's what creates the current, and the current is what causes the radiation. So this drawing shows magnitude, not phase. This is a resonant half-wave dipole with current and voltage in phase everywhere, although they have different locations for their maximum and minimum. And on harmonics, you can extend the wire. Let's look, here is our original feed point right in the middle. And this was the original dipole that I just showed you. And we still have the dashed line for voltage and the solid line for current. There, the magnitudes change along the antenna, and each one of these sections is a half wavelength long. So it's 3 half-wave dipoles connected end to end, fed in the middle. So let's talk about impedance for a minute. What is impedance? Impedance is basically how much you get for how hard you push. And how much you get is current, and how hard you push is voltage. So if you divide voltage by current, that gives you impedance. That's all it is. How hard you push on the electrons for how much electron motion you get. So the ratio of voltage to current is very low in our original feed point because the voltage was at a minimum and the current was at a maximum. Well, at the original end of the dipole, let's see here, here, and here, we have high impedance because we have high voltage and low current. So that's a high impedance point, and that repeats every half wavelength along the antenna. Here's another low impedance point. Even though the current is flowing in the opposite direction, it's a magnitude measurement. And so you have high current in either direction and low voltage, you will have low impedance. Same thing over here. So this is a half wavelength antenna used. It's technically, we have 3 half waves connected end to end here, but you could take the original antenna, half wavelength long, and use it on its third harmonic. And many of us have used a 40-meter dipole on 15 meters that way. And this is a complicated drawing, originally from ON4 alpha alpha, and it shows for the first 8 harmonics. This is the fundamental here, down at the bottom, conveniently numbered. Here's our current maximum, we left the voltage out of this because it just made it too complicated to look at. So here's the current, low at the ends, high in the middle, low at the end. And so this is a low impedance point. And in the previous slide, we saw that we had a low impedance point on the third harmonic in the center, and every odd harmonic is a low impedance point in the center. You could hook a coaxial cable here and have a reasonably low SWR, 1, 3, 5, 7. Well, on the even harmonics, however, you have low current in the middle for all of them. And this is the second harmonic, the fourth, the sixth, and the eighth. And you have a high impedance point in the center. So all of the odd harmonics, you can use a half wavelength dipole on its odd harmonics with a low impedance at the feed point, or you can use it on the even harmonics with a high impedance feed point. But there is a spot along the antenna where the impedance, if you can sort of unfocus your eyes a little bit, you can see that the current is sort of moderate there. And if you recall, the voltage is also neither very high or very low. So you wind up with impedances right around this point that are somewhat similar. And if you are judicious in choosing the exactly right point, you can find a point along the antenna where it has a similar impedance on several bands. And that is the origin of the off-center fed dipole, or OCF. So what we find is points with similar Z, feed point Z, for off-center fed. That's what OCF refers to. On multiple bands, you can find a point with 100 to several hundred ohms of impedance. And so W4RNL, a silent key, but great writer of antenna articles, defines the off-center dipole with several dimensions. The overall length is L, and the distance from one end to the feed point is D1, and from the feed point to the other end is D2. And then from the feed point along the longest portion of the antenna, you have half of L, so here's the midpoint, and what's left is D3. So what you find is that different combinations of D1 and D2 give you different types of impedance. So then you use an impedance transformer to reduce the impedance to somewhere around 50 ohms, so you can hook up coax to it, and it will work on several bands. You can find designs with a 2-to-1, 4-to-1, 6-to-1, 9-to-1 impedance transformers. They're all possible. And so you choose the feed point location so that SWR is acceptable on multiple bands, generally less than 3-to-1. So the internal antenna tuner, say that 10 times really fast, the internal antenna tuner can generally handle an SWR of 3-to-1. So if you can find this point on the antenna, use an appropriate impedance transformer, then you have a multi-band antenna. And this mind-bending drawing shows SWR as in different colors for different bands, and VSWR is on the vertical scale here, and this is percent offset along the antenna, and this is the point on the vertical scale where SWR is 2-to-1 or pretty close to that. So what they found was there are several common ratios of D1 to L. One is 29% offset D1 to L. That's about 30% along the antenna. You use a 4-to-1 transformer, and you can typically make that work on 80, 40, 20, 15, and 10. What they've done is they've found this point on the antenna that's about 30% along the antenna, and all of the SWR curves are in this similar area below 2 to 1. Other common designs, if D1 to D2 is about 1 to 3, that's a quarter from one end, and another is 20% from one end. And it depends on which bands you want the antenna to work on, how high it's going to be off the ground, etc. All these things affect the feed point impedance, just like they do on a regular center-fed dipole. If they're really close to ground, if they're very far from ground, if they're near other antennas, is your ground conductive or is it very dry? All these things affect antennas, and they also affect off-center fed dipoles. But now you understand how the off-center fed dipole works. Okay, there's one other point along the antenna with similar impedance, and that is the end. It's high impedance at the end on all of the bands, on all of the harmonics, 1, 3, 5, 7, 8, 6, 4, 2. We have low current and high voltage at the end of the antenna. So if we can transform that high impedance down to something that coaxial cable likes, well, we could use it on all of those harmonics, on all of those bands. So at the end of end-fed antenna, at the end of that dipole, ZEF or Z-end or Z-end fed, it typically ranges from about 1,000 to 5,000 ohms. You would think, oh, well, it's infinite because there's zero current. And it isn't really zero because there is enough capacitance between the antenna and the ground and other structures and other antennas that some of that current can actually flow and leak off the antenna. So the current is not zero, but it's not very much. So you wind up with the high voltage divided by a very low current, and that gives you a high impedance. Typically, you find the range is 1,000 to 5,000 ohms. Trying to get an impedance of 5,000 ohms or more at RF is actually quite hard to achieve because it doesn't take very many picofarads to allow some current to leak and lower the impedance. Just getting your hands close to an antenna. I know some of us have touched or gotten close to an antenna while testing it or something, and the person looking at the SWR meter or something says, oh, when you got your hands close to it, the SWR went up and down, and that's because of the capacitance between you and the antenna allowed some of the current to flow to you, and that changes the feed point impedance. So it's actually quite hard to get a really high impedance. There's a lot of ways for the current to leak off through small capacitors. So we also have problems feeding antennas at high impedance points. First, that means high voltage. The voltage is going to be about 20 to 100 times higher than at a 50 ohm point on the antenna. That can cause problems. It can cause safety problems for starters. Don't ask me how I learned this, but it involved transmitting with a whip antenna too close to a tree, and I sort of set it on fire. It was smoking a little bit. We didn't start a forest fire or anything, but 100 watts is sufficient to cause a leaf to emit some smoke. And then capacitive coupling is always a problem because at this high impedance point, and you move the antenna around a little bit, suddenly it's closer to the ground or farther from the ground, or another antenna gets close, or a vehicle or something, and you've got capacitive coupling, and that lowers the impedance, and that upsets the impedance transformation. So there are some issues with feeding things at the end. Here are some typical in-fed half-wave half-wave antennas that you'll encounter in the amateur literature. Over at the left is one of the original in-feds, and that was a ZEP, named for the Zeppelin, because what they would do is hang this antenna half wavelength long from an airship, and they would feed it at one end because the other end was just dangling around below the airship. And they used tuned feeders to lower the impedance so the transmitter could couple energy into it. And no, this is not what happened to the Hindenburg to light it on fire, but it was very common in airships. Right next to that, here in the middle, is the half square, where you have this is a 40-meter design. You have a quarter wavelength piece of wire here and a quarter wavelength wire here, and they are connected with a half wavelength wire in the middle. It's not the half wave in the middle that does the radiating. If you look at the current, it's flowing in one direction on this side and the opposite direction on the other. So the radiated fields from the center portion cancel out. But the currents are flowing in the same direction in these two vertical sections. So what you have is two vertical elements, quarter wave elements separated by half wavelength, and you feed it at the bottom of one of these vertical elements. And it's open, so it's at the end, it's high impedance point. Here's another one. The bobtail curtain is popular, and you have basically three. It's sort of like two half squares combined into one antenna. And a popular method of driving it is to put a parallel LC circuit at the bottom, tune it so you get a resonant point, and then you move this tap around on the coil, and it acts as an auto transformer, and you move the tap until the SWR is where you want it. And this is a bi-square. It looks like a loop, but it's not. It's two antennas, two sections that are made into one sort of an inverted V on its side. And there's another one over here. And the arrows show the way that the current is flowing. And you can see what you have is effectively two horizontal current elements, one above the other. And this is a popular portable antenna for the higher frequency bands where the height is not very big. It's manageable. Anyway, so now we have three identical antennas: the half wavelength dipole, the off-center fed dipole, and the in-fed half wave. They're basically the same antenna. If you look at the wire, you can't tell any difference. It's exactly the same piece of wire. And these are fed at different points on the antenna for reasons of convenience. Maybe you want maybe you can only feed it at one end. Maybe you want to feed it in the middle. Maybe you want the off-center fed for whatever reason. Now, you hear a lot, and I've been guilty of this as well. People overselling this equivalence, and you say, oh, it's the same antenna. It is fundamentally the same piece of wire. Okay, and on the fundamental, where you only have the one current maximum in the middle, they are, in fact, the same antenna. And they have the same gain and the same radiation pattern and all that, minus whatever transformer losses or something like that. And there's no difference in gain or radiation pattern on the fundamental. As you raise the frequency, what happens is the current distribution along the antenna is no longer symmetrical about the midpoint. It starts to act like a long wire, and so the pattern, the gain, is sort of skewed to one end. You have higher current close to the feed point, and it sort of tapers off at the higher current maximum. So what starts out as this nice, broadside figure eight, it breaks up into sort of a cloverleaf pattern, and then at the higher frequencies, one side of the cloverleaf sort of gets squashed. That's a technical term, squash. And so it's not symmetrical anymore. Feed point location does matter if you have multiple current maxima along the antenna, and that happens in non-resonant operation. Maybe it's not right on the harmonic, and you're just forcing some power into it, and the higher harmonics. So all three of these antennas, the center-fed half wave, the off-center fed dipole, and the in-fed half wave, they all have their drawbacks and they all have their features. So you go back to your antenna system requirements, and being an engineer, I use that word a lot. And you say, well, I got to worry about transformer expense. Do I even want a transformer? What about feed line loss? At high SWR, am I going to lose my watts heating up the feed line? How many supports am I going to have available? If you're at home, you might have one set of supports. If you're in a park or a field day or something like that, you might only have one. How does this work? If you're backpacking, climbing up a mountain or something like that, weight is also a real concern. So you've got to balance all these different requirements to pick the right one. Some people have all three available to them: half wavelength dipole, an off-center fed, and an in-fed, and they use it for different applications. Let's talk about feeding the end. Hey, what's the deal here? I wrote a column in QST magazine a few years ago about there is no such thing as an in-fed anything. You cannot force current into just one wire at the end of the feed line. The rest of the current has to go someplace. And so where does it go? We attach the feed line at the end of the antenna, and by golly, we worked some people. We were able to tune it up. Everything seems to be working. What are you telling me? It doesn't work. It can't radiate. Well, it's because you're not technically right at the end when you attach a feed line to the end of an antenna. And Roy Llewellyn, W7EL, the guy who wrote EasyNet, he analyzed an in-fed wire. And you can see that over on the right. He took an antenna, a regular half wavelength dipole, and that is labeled antenna right here. And the red curve is the antenna current along the antenna. We've already seen that 2 or 3 times in the presentation. Okay, but what he found was if you attached a feed line, and he included the model of the feed line, he didn't just simulate it, he actually created a twin lead feed line, open wire, parallel conductor feed line. You can see that here. Okay, and he connected it to the antenna and he modeled the whole thing. Okay, and what you see is, oh, right here at the end, this current doesn't go to 0. It goes to 0 over here at the end that you can't see because my face is over it. But over here, it's not 0. There is some additional current flowing. Where does it go? So he looked at the current in each of the feed line wires, and he found that they are a little bit different. And this difference, the curves aren't quite the same height. And that's common mode current. It flows on both of the feed lines. It's effectively an average current that's non-zero along the feed line. And that's where the missing current is. And that's exactly the amount by which this current here, the end of the antenna, is not 0. It's flowing along the feed line. So what you really have is a bent antenna. And so the current is flowing along that. The current has to go somewhere. So it's end-fed. Yes, it looks end-fed, but it's not fed at the electrical end. The electrical end is somewhere else. So your feed line is part of the antenna. Well, I put a choke at my antenna, and so there's no current there. It got blocked. If I can't use the feed line, then what? Well, then you might have to use a ground screen, radials or mesh. Over here in the States, we call it chicken wire or hardware cloth. I don't know what the appropriate British term is, but it's a wire mesh. And you can put that down as your ground screen. The current will flow along a coaxial cable shield. If you understand the skin effect, you know that the inside of a coax shield is electrically different than the outside of the coax shield. And so the common mode current in this case flows along the outside of the coax cable shield, and it radiates just like anything else. Current flowing along a conductor will radiate. You can put on a counterpoise wire, and we'll talk about that in a little bit, or you can connect it to the earth if you want. You can earth your antenna. Okay. So let's talk about this transformer business. Here we are at the end of the antenna, and we've got this high impedance, and we're going to feed it somehow at the end. How do we do that? So what really made the in-fed half-wave antenna practical was a really good transformer design. That's what makes it work. There have been a lot of attempts. There's a lot of bulky things. We saw the tuned LC circuit, stuff like that. But Steve Dick, K1RF, great call sign. Steve analyzed all this, and he really put all the pieces together, and he is the guy that sort of kicked off this in-fed half-wave business. And if you Google Steve Dick, K1RF, in-fed half-wave, you'll see his original presentation, and it's worth downloading and watching or just reading. And this is a slide from his presentation. It was done in 2017, and this is a presentation that was adapted by K1TA. He uses a 49-to-1 transformer. That's an impedance transformer that it has a 49-to-1 primary to secondary impedance ratio. The primary has 2 turns. The secondary has 14 turns. And so 14 divided by 2 is 7. The impedance ratio is the square of the turns ratio. 7 squared is 49. And so you have a 49-to-1 impedance transformer. And the blue is the blue wire is the secondary. The red wire is the primary. And he has some information on the design there. And I provided these slides as a PDF to the club, and they can be posted on your website, distributed, emailed, whatever. There's no copyright for this. Feel free to share it. The toroid core is somewhat special. You use a type 43. And some of you who are RFI mavens will go, wait a minute, 43 blocks RF current. Well, not quite. Below VHF, it's a rather effective, what they call an inductive core. In other words, for energy storage and inductive uses, and it works quite well as a transformer at HF. Above HF, once you start to get to 6 meters and up, it begins to be lossy, and it's used as an EMI suppression core. And then down at the bottom, you see this little 100 picofarad capacitor. What is that for? Well, the windings all have some inductance, and as you get higher and higher in frequency, primarily above 20 megahertz, the inductance starts to upset the impedance ratio, and so this capacitor swamps out some of the inductance, and so it's called a compensating capacitor, so that the impedance ratio stays consistent all the way up through 10 meters. And you'll notice that the primary turns are twisted with the secondary turns, and that's to have the best coupling between the turns on the transformer. Now, you'll note also there's a crossover turn where you wind 7 turns and then you go across and under the core, through the core, that's turn number 8, and then another 7 to get to the other side. That doesn't really have any magic electrical characteristics, but what it does is it makes the output be on the opposite side than the input, and that's mechanically convenient for constructing the impedance transformer and the antenna. Okay, so you need to pick the right impedance ratio of the transformer, whatever it is, so that the SWR is reasonable. The turns ratio is fixed. You're not going to change it, although some people might use a switch to select different windings. Mostly, we don't want to do that. So you've got to pick what kind of an end impedance you think you're going to get. It's going to be somewhere between 1,000 and 5,000 ohms. Well, if you ask an engineer to pick a value between 2 two values, we often go, well, what we'll do is we'll use the geometric mean. It's a very common function. It tends to reflect the way things actually work in the real world. So we take 1,000 times 5,000, and we take the square root of that, and we wind up with 2,236 ohms. Okay, so we call that the optimum ratio would be between this geometric mean impedance divided by 50, and we get a turns ratio, we get an impedance ratio of 45. Okay, 45 isn't the square of any integer, so we pick the closest integer squared ratio, 49, which is 7 squared. So what do we get across our range? Well, at 1,000 ohms divided by 49, we get 20.4 ohms, which is an SWR of 2.45 to 1. At 2,500, we're almost right on, and we wind up with 51.2 ohms, an SWR close to 1. And at 5,000 ohms, it divides to 102 ohms, and we get an SWR of 2.04 to 1. So we get this nice curve that goes from 2.45 down to 1 and then back up to 2 across our entire range of impedance. And here are some graphs. The InFed is available with, I've seen all kinds of products with 9 to 1 transformers all the way up to 81 to 1 transformers. There are designs you can build yourself. There are products you can buy. And the impedance of that wire is going to change over a wide range. It's going to change with frequency, affected by ground and height, nearby conductors. So what we found is that 49 to 1 is a good compromise over the expected range. And here are some graphs showing that SWR variation for different kinds of transformers. This one up at the top here, that's a 9 to 1. You can see it's pretty good if your end impedance is down around 1,000 ohms, but boy, you get up to 5,000 ohms and the impedance is close to 12 to 1. And so this is 9 to 1, this is 16 to 1, 25 to 1. So 3 to 1 turn ratio, 4 to 1 turn ratio, 5 to 1 turn ratio, 6, 7. So here's our 49 to 1 impedance transformer. Now look, it's nice, goes from just above 2 down to 1 at 2,500 ohms, and then it comes back up. Spreadsheet graphing is a marvelous thing. And then you can go to 64 and 81 to 1. 81 to 1 has the opposite problem of a 9 to 1. At the very high end of the range, 5,000 ohms, it does really good. It's pretty close to 1 to 1. But at the low end, it starts to increase. Some of this is masked by feed line loss. If you get really high SWR and it's a ordinary lossy coax, the impedance at the transformer, the SWR at the transmitter, can look a lot better than it does at the feed point. But at any rate, 49 to 1 is a good compromise, and so that's why it's a popular design. Here's what one looks like, and you can see, here's our compensating capacitor, and you use a high voltage ceramic capacitor because there could be some high voltages there, and you want an efficient capacitor so it doesn't have loss. So you use a high voltage ceramic capacitor. Here's your input connector, an SO239, and here are the twisted turns, 7 over here, and then there's this was more than 7, and then there's a crossover, and there's 4 more. This design doesn't have the antenna connection on the top of the box here. This is a point where you suspend it, where you hold it up. It's over here. So you can distribute the turns around the core to come out where you want. And this one has 4 over here and 10 over here. Okay, and this little thing here is a vent. If you put these out there with without any ventilation in the box and you run them at the maximum value of current or of power into the transformer, they'll overheat. So you need a little ventilation there. This one has 2 cores, and the cores are held to the box with a nylon cable clamp, and that's pretty common as well. Okay, so here we go back over here. This is the schematic. Here's your coax, here's your RF connector, here's the little compensating capacitor, here's the transformer, this is the core, and so here's the wire attachment point. And remember, the transformer's got to have two connections, so you get current in and current out. Where's the missing current path in this? And so you look really, really closely and you will see this little wire here, and that's between the flange of the RF connector and the ground terminal. And so here's the missing path. You have your antenna, it's connected to the transformer. The other end of the transformer winding, the secondary, is connected. It's jumpered directly to the ground connector of the SO239. You've got your capacitor across the primary. This is the missing path. This is where that common mode current will flow. Okay, so what are you going to do about that? That's where the counterpoise comes in. So what is a counterpoise? It's a very old word, and if you go back to the early days of wireless, counterpoise really refers to a thing that replaces the missing part of the antenna. That's basically it, and couples it to the earth. And the old days were really long wavelength signals. You will see big screens that look like spider webs that are stretched out from the base of the antenna, and they're elevated up overhead, and that was the counterpoise. It can be a wire, a screen, a radio. It's just the other part of the antenna. It's not a mystery or magic or anything like that. It's just the missing part of your antenna. If somebody says, oh, I got a counterpoise wire and I laid it on the ground, what that means is part of my antenna is laying on the ground, and the counterpoise is just that missing part. And why you would want this, why you would want the coax shield or ground screen or a counterpoise wire is you want to stabilize the impedance a little bit at the feed point. If you're right at the end where the impedance is the highest, that's where it's the easiest to affect by distributed capacitance or height above the ground or something like that. So by moving in a little bit, about a 20th of a wavelength along the antenna, and that making that your counterpoise, then you stabilize the impedance. It's a little bit lower, it's not greatly lower, and you just get a more predictable performance. Okay, what makes up this counterpoise business? Well, here's a typical design. Here's our impedance transformer down here. It's about a few feet above the ground. You've got a stake or you've tied it to a post or something like that, and there's your in-fed half-wave transformer, and you could do any one of these things. You could just let the feed line be the counterpoise. Just lay it on the ground, and the common mode current will flow along the feed line shield, and that becomes your counterpoise wire. The currents inside the coax don't even know that extra current is there. They're independent. You could drive in a ground rod. You don't have to, but you could. Or you could lay out a counterpoise wire, less than a quarter wavelength long. It's not tuned. It's laying on the ground, so it's coupled pretty much to the lossy median of the ground. Typically about a 20th of a wavelength. 5 or 6 feet is a typical value. And so here's your antenna wire. It goes up here, and I said here's the 6 to 20 feet counterpoise wire. Okay, and you can hold it up in the middle, you can bend it over, you can make it an inverted V, whatever. But if you put a choke balun on the feed line, say you are operating from some kind of a park table or something like that, and the antenna feed point isn't very far away, and you transmit and you go, oh, I've got RF in the station, so to speak, and it's upsetting my computer or making a hotspot on a key or something like that. So you put a choke balun at the feed point, and all of a sudden it's not working very well. Why? Because you cut off your counterpoise. So that's when you add the counterpoise wire. I've used 5 or 6 feet, but 6 to 20 feet. And you've got to give that missing current some place to go. And if it can't flow along the feed line, then you give it a counterpoise wire or a ground rod. And if you do use a counterpoise wire, you leave this end open, okay? And if you leave that end open, it will also be at a high impedance point. And a high impedance point means high voltage. And if you're walking around in your bare feet and you step on this high impedance point while you're transmitting, you will confirm, you will verify that it is a high impedance point and burn your foot. You'll get a little RF burn. Don't ask me how I know this, okay? Just you'll have to take it on faith. But an open wire there, it will be at a high impedance point. So keep it away from dogs and cats and kids and curious onlookers. All right, so let's go back over the NFET halfway. What makes it so popular? Why is this such a common antenna? Well, it's very useful. It's efficient. It's a good radiator. It doesn't require a lot of trickery to get it to radiate. It's a straight piece of wire. Electrons accelerating in a straight piece of wire going back and forth. That is what causes electromagnetic waves to be created and radiated away. It's also very light for packing if you're going out for a walkabout or some kind of portable adventure or a field day or what have you. It's very light, easy to carry. It only requires the one support. You can leave the impedance transformer, actually just lay it on the ground if you have to, and then run the wire up in the air to some kind of convenient tree or pole or whatever. Some people take a multi-section spider beam pole or the like and put that up and use that to hold up the middle or the end of the antenna. So the 160 to 10 meter version, it's about 260 feet long, that's kind of long for a either the typical city or suburban lot or park operation. There are versions of this thing that use loading coils to allow you to get on 160 meters and not have the full length. Most popular are the 80 to 10 meter versions. It's 132 feet, fits in the backyard. I believe that would be a garden in British terminology, and I have one at home, and it goes up about 20 feet and over about the rest of the way, and it winds up about 50 feet in the air. You can also cut this thing about halfway along and stick in a capacitor of about 300 to 500 picofarads at the midpoint, and it will raise the resonant point on 80 meters up into the 75 meter voice band. You have to take it back out if you're going to go back down to 80 meters, but you can you put an insulator there and a jumper that you can replace with the capacitor when you want to operate on 75 meters. It does not affect the upper bands hardly at all because the reactance of the capacitor drops with frequency. So on the higher bands, 40 and up, the capacitor doesn't really affect antenna performance. You can also use this particular version of the antenna as a quarter wave ground plane on a 160. So what you do is you disconnect the impedance transformer entirely and drive the antenna at the feed point directly with coax through a tuner or a series capacitor, and you use ground radials or a ground screen. You can also load it with coil if you want. And so that's what I do when I have my 80 to 10 meter version at home. And here comes the 160 meter contest. I go out and disconnect it. I use a series capacitor. It's about 2,000 picofarads. And I roll out 3 of these rolls of metal mesh under the antenna and connect them to the shield of the coax. And boy, that works just great. It's just a bent over quarter wave vertical. Then you can put it all back together and go back to 80, 10 meters. The 40 to 10 meter version is very popular for portable and backpacking. It's only 67 feet long, and there are versions with loading coils to get you to 80. You can clip on little resonator sections for 60 meters and that kind of thing. So very flexible antenna, and you can put the whole thing in a small candy tin about this big, and that is great for backpacking. 5-watt. You only have to have one small core in your impedance transformer. It works quite well. If you're going to make your own, if you're going, I can do that, and of course you can. You download and study the K1RF presentation. Just Google K1RF InFed halfway presentation, and you'll find it. Then you put it up. Be prepared to trim the length, like with any antenna, so that it works acceptably on the bands that you intend. You'll see some designs about 6 feet from the transformer. They have a 6-turn loading coil. It's about a microhenry or a microhenry and a half. And what that does is it makes the antenna look a little longer on the higher bands than it would without the coil. And those of you that used a 40-meter dipole on 15 meters know that, well, it was a little high in the band on 15 meters because there's no endpoint on 15 meters, and that changes the antenna a little bit. So about at the ends of where a 15-meter antenna would be on a dipole, you add a little like a capacity wire or a little twisted bow tie or something. And on 15 meters, that brings the resonant point back down to the bottom of the band. So that's what this 6-turn loading coil does near the feed point. For toroids, remember, type 43 material, inductive at HF, lossy at VHF and above. Use at least two of the 2.4-inch outside diameter cores for QRO. That's 1,000 to 1,500 watts. If you're going to run 100% duty cycle like FT8 or RTTY or something like that, use 3 cores, or you'll find out that you should have. And at 100 watts, you can get away with a single 1.4-inch OD core. And a QRP, just one of the little 1-inch guys for QRP works just great. You have to use enameled wire, not bare. You don't want the wire shorting to the core, and you don't want the primary and the secondary wires in direct contact with each other. You can use insulated wire, but the insulation can't be very thick and still get the same effect of twisting the pair of enameled wires next to each other. And the compensating capacitor should be at least 3 kilovolt rating. Murata Erie, M-U-R-A-T-A, makes these capacitors. TDK also makes them. You can find them online in your component websites. All right, you're going to use this thing, so watch out for high voltage at the feed point. It's at the end. It's high impedance point. It'll have high voltage. Even if you have a counterpoise wire, it'll still have high voltage at the feed point. So you want to make sure that onlookers, visitors, if you're in a park or something like that, you want to make sure people can't touch it. If you're at home, you want to make sure that casual passersby aren't going to reach out and touch it, or your pets or something like that. Or a helpless leaf from a tree that would get too close and be caught on fire. You can install it as a sloper with the feed point at one end low, and then, if I can do this right, and the other end high. So it's just a sloping wire. You can do it with a center support, so it becomes kind of like an inverted V, and you can put it up horizontal. Remember that ground will affect, the proximity of ground will affect the antenna's performance a little bit. So you may have to trim it or reorient it a little bit to get all of the bands where you want. And a coiled coax choke will help with RF in the station if you're in a portable situation. This is described in the RSGB handbook and also in the ARRL handbook. Just a few turns of coax coil that creates enough inductance to often tame the current trying to flow back down the cable. And always use the good quality coaxial cable. RG174 is really only useful for portable QRP use with very short cables. It's quite lossy, but it's also very small, about 0.15 inch in diameter, and it's light, which is sometimes very important. So you would want to use a short length. RG58 or can work up to 100 watts. You can use it up to about 100 feet. But boy, there is an awful lot of poor cable out there. So use the good stuff. You work too hard to build the antenna and build your transmitter and get your station working. Don't throw that performance away with saving a few bits on your coax cable. And on QRO, you want to use RG8X or RG213, and if you're going to have a longer run than 100 feet. Okay, so let's summarize. First of all, the in-fed half wave. It's a half wave dipole and it's fundamental, but it's fed at one end. Okay, it's just if you play guitar or a stringed instrument, you know that you can make that string vibrate pretty well, plucking it close to one end, but it's a very hard it's much harder to get the equivalent volume out of that string if you pluck it near the end as opposed to closer to the middle. Okay, it's the same basic antenna as the half-wave dipole and off-center fed dipoles on the fundamental anyway. And as the higher harmonics come along, it radiates more like a long wire, sort of off one end. So you have to be aware of that. You can make it operate on multiple bands because of the consistently high impedance at the end and design your transformer for that. But the impedance transformer has to be well designed. You have to take into account the inductance of the winding, the core material, the number of turns, all that kind of thing. And you have to balance your trade-offs with other types of dipoles, of weight and the installation and all that kind of thing. So I hopefully hit all the high points here on the in-fed half wave, and I would be happy to take some questions.
Thank you very much, Ward. Very comprehensively covered. I don't know how many people watching find the N-fed half wave a really effective antenna, but as I said, I have, and still it's my aerial of choice really for all sorts of things, both for portable stations. I mean, we're going to be doing, as you may have heard earlier, we're going to be doing the international lighthouses and lightships on the air earlier on, later this month, and we're going to be using one there because it's ideal, it's very lightweight, it's easy to put up, temporary, for something quite relatively portable or temporary, and it just does a pretty good job. That's after trying all sorts of antennas over the years, like Wyndham's and things like that. I don't pretend to know all of the detail about it like you do, but it's certainly you've helped us understand how it works. So if
are you going to be operating at the bottom and then using the lighthouse as the pole, or are you going to be up at the top of the lighthouse?
I'm trying to think how it's used now. Yeah, we put the transformer at the top. We pull that up with a halyard, and then the aerial we can take it to fields. Luckily, this lighthouse has got fields all around it, so we can easily stake it safely into the ground around without anybody getting near it. I think so.
Good.
Yeah, it's very. Pardon?
I've done the lighthouse contest several times when I lived out in Washington State, and it's a fun contest, a beautiful time of the year, and I loved it operating from Point Robinson because we could see 3 other lighthouses and therefore could activate 4 at once. It was a lot of fun.
Yeah, it is good. I hope lots of people will support it and help us operate it. Now, we've got already a couple of questions for you, Ward, but as always, if you have any questions or comments to make about the N-fed half wave or anything that Ward has talked about, this is the time to enter them either on BATC or Facebook. So first up, a question from Martin G7UGB, who asks, I run my 49-to-1 at the top of my aluminium pole and the coax comes down from that to the shack. Or should I be keeping the 49-to-1 at the bottom of the pole, or doesn't it matter?
Okay. Yes, it can matter. And the higher you can get the current maximum above ground, the stronger your radiated signal will be. So if you have the ability, the wherewithal to get your impedance transformer all the way up at the top of a pole and then stretch out the antenna, particularly on the fundamental, try to get the current maximum as high above ground as you can. Now, if you're putting the impedance transformer at the top of a pole, you have to make sure that you have some counterpoise there to stabilize the feed point impedance, and that's probably going to be your coaxial cable shield. But obviously, it's working for you, and it's not broken, so don't fix it. But you should be aware that you do have some common mode current on the outside of the shield, and probably coupling to the pole as well. Back to you.
Okay, yeah, thank you very much, Ward. Hope that helps you, Martin. Next up, Rick M7GMT asks, with the missing current, in inverted commas, the missing current being dumped into the feed line or ground for half of the cycle, aren't you essentially wasting, or at best misallocating, 50% of your output power?
Oh, not 50%. No, not at all. The actual common mode current is fairly small. You're at the high impedance point of the antenna, and so that's where current is low normally. And so the common mode current, if you have coaxial cable, will flow on the outside of the cable, not inside. And so if your cable is laying on the ground, yes, it will couple somewhat to the ground, but it's a small fraction of the total current in the antenna. Your main signal comes from the current maximum that's up along the antenna somewhere. On the fundamental, that'll be 50% of the way along the antenna, for example. On the second harmonic, it'll be there'll be two current maximums, one quarter of the way along the antenna and the other 3/4 of a wavelength along the antenna. So you get the idea. But no, you're not dumping a lot of your power into ground.
Okay, thank you, Ward. Another question now, this time over on Facebook from Tom Miller, JXQD. He says, I was going to ask loads of questions, however, the talk has answered most of them. So he has, his long wire is 43 meters or 142 feet long. He has a ground spike and a coax coil at the balun. He trims the resonance with an old Yaesu FC902 ATU, and he says he's worked 10 to 160 meters without problems. His only question left is from 9:1 to 81:1, which three should I build for experimentation using the existing 142-foot wire?
Well, let's see. I would try a 9:1, and then well, let's see. It's hard to get away from the 49. If you only had to pick three, I guess I do the geometric mean trick again, you know. So 9:1, 36:1, which is 6:1 turned ratio, and then an 81:1, and see which one works best. And then wind 3 with the one that you've selected, and then 1 to either side of it. So say, for example, 36:1 gave you the best performance out of those 9, 36, 81. So then you'd wind a 25, a 36, and a 49 and see which one works best. So you'll be winding some wire, but it's a fun experiment.
It is good. Good to see so much interaction from you at home as well on this. I can tell you, Lord, you know, there's a lot of people. We don't normally get as many people watching live now as obviously we did a few years ago. But I can tell you that there's been a solid 50 people watching over 2 platforms tonight, and there's a lot of questions. So next one for you, or really this is a statement, I guess. Malcolm G3PDH, who's actually the organizer of the Lighthouses on the Air, and he uses this. He says, thank you for a very comprehensive talk and explanation. Could you please reiterate again how you use it for 160 meter as a quarter wave, so top band?
The 160 meter, yes. You're going to turn it from an in-fed high impedance feed point to a base-fed quarter wave. And so essentially, it's a quarter wave vertical, just like quarter wave ground plane, that you can use the same wire as a quarter wave on 160 or as an in-fed half wave on 80 meters, and then on the harmonics going up. So the way that I found this to work best was I disconnected the antenna wire completely from the impedance transformer. You don't use the impedance transformer in this configuration. It's just a quarter wave vertical. And if you've got an antenna analyzer, you can measure the impedance at that point. Remember, you have to have your ground screen. I used the 3 rolls, 10-foot rolls of mesh. You can put out radials, whatever. Install your ground screen, connect it. Your feed point is connecting between the ground screen and what's left of the in-fed half wave, which is the wire. And so you measure the impedance at the frequency you're interested in, like 1.820 megahertz, for example, and then you can either design a matching network to, like an L network, to match it there. Sometimes you get lucky, and all you need is a series capacitor because it will be slightly long electrically. That's what happened to me. I had this, I measured it, and it turned out to be almost dead on 50 ohms, but it had a significant amount of reactance. And so the reactance was inductive. I said, okay, I'll put a series capacitor there, and that'll tune out the inductance. You can use a variable capacitor, or you can use a fixed value. And I got lucky, and I calculated the value, and it said 2,000 picofarad, plus or minus a little bit. And so I went to the junk box, and there was this mica capacitor from World War II that had been sitting there waiting for all these years to be used for something. And I put it in series. I only run 100 watts with this antenna. It was perfectly happy. Got SWR about 1.1 to 1 at 1.8 megahertz. Or you can use an antenna tuner. Just put a portable auto tuner there, or a manual tuner, and cover it up so it doesn't get wet. That works amazingly well. You're just using the wire as a quarter wavelength, base-fed, ground-mounted vertical. And, you put out a ground screen. The ground screen doesn't have to be taken up when the main in-fed half wave is used either. It doesn't really hurt it. It doesn't affect it that much. So hopefully that answers the question.
Yeah, I think so. Thank you again. These are really good questions. You mentioned in your talk that Steve Dick K1RF, is he credited then with this design basically?
Well, the design has been around for a long time. What Steve did was he said, okay, I'm going to figure out how to make this impedance transformer properly. And he selected the ferrite mix, and he experimented with the turns ratio and came up with the 49 to 1 transformer, and then added the small coupling capacitor, which cost pennies, and made the design electrically sound. So I give him full credit for making the antenna practical, although it had been around for many years.
Yeah, I noticed on his drawing that you showed on there, I wrote a note that it was 2017, which seems remarkably recent, really. But obviously, as you say, it's been around for a lot longer. I've got one other question. We've got nothing else from our audience, but such a comprehensive talk, as everybody said, and lots of compliments, by the way. My question is that although there's a lot, I mean, we can make one ourselves, we could go out and buy the parts, but there's a lot of pre-made ones at quite low cost out there. But there was one in particular that was recommended to me. I had a particular special event station do it very short notice a few years ago, and I asked our main antenna guru here, N0AX, and asked him, and he said, well, the end-fed halfway is going to be your best friend on this particular job, to do it quickly and easily and put it up and everything. And he suggested a particular one made by My Antenna, who I'm sure you know are your side of the pond. from Florida. And that universally, it does seem that many people recommend them, and they do seem to work rather better than many of the others on the market. Now, apparently, I have never tried to do it, but if you open it up, it's full of resin and it's been potted and things. So can you take a stab of a guess of why theirs seems to be one of the best, if not maybe the best commercial one on the market?
Well, let's see. I know there's Vibraplex sells the InFeds models, and there's my antennas. There's several manufacturers in Europe and all that. Antennas are very subjective. And when you say best, do you mean most efficient? Do you mean lightest? Do you mean that it went up and down and didn't break?
Good question. Yeah, good point.
Yeah, there's lots of things.
I think performance overall, I think, was Steve's main suggestion, just based on his experience and all. And I mean, actually, I should qualify this by saying that Steve designed one for our club, a kit, made it to make it really easily available, very, very little money, £15 we sold this complete kit for, apart from the long piece of wire, which is about $20, So it was about as cheap as it could be. We never aimed to make any money from it. It was just to really make it easy for everybody, and did a whole project based around it. But even so, he said that, for the best performance that I could do, given the time I had, just a little time to do this, that was one of the best ones he'd found anyway. And as you say, all these things are subjective reviews and things. But I think performance-wise, it may be slightly better at covering, especially up to 80 meters around there.
Okay. Well, it gets back to the impedance transformer, and I have not disassembled, a half dozen different ones to look at. But first of all, you have to use the right number of cores, and you have to use the right mix. If you don't, if you scrimp on the core, maybe you only use one instead of two, or you use maybe type 75 or 61, perhaps. If you don't use the right ferrite, you're going to get losses there. And is the transformer wound so that the primary and the secondary are very tightly coupled? Those wires have to be right on top of each other. If you get sloppy with the transformer winding, the coupling won't be good, and you don't get the consistent transformation, and you can get some losses in the core there. I've seen a couple of units where the core breaks free inside the box because it's not secured properly, and it doesn't really change things much electrically, but things can rattle around and break loose. And then there's the selection of the compensation capacitor. If you use maybe a film or an inappropriate type for transmitting, then that might not present a consistent impedance transformation over the whole HF range. And it also depends on whether you're testing at 80 and 40 meters or up at 12 and 10 meters as well. So there's a lot of variables to that, but I think primarily it's selection of the core and the attention that's paid to how the windings are put on the core that really make the difference.
Make the quality of it, yeah. Well, as you said as well, many times in this, and as Steve's kit and design said as well, this is an ideal antenna to make at home as well. It's very low cost, easy to tinker with and play with, isn't it? And just to adjust and try and get the best from it. So we should really be encouraging everybody. It's one of those antennas you really should try and make yourself. If anybody's watching this, by the way, and you weren't around the club when Steve published his kit, then I can certainly send you the PDF, which tells you where to buy everything from. But Ward, it's been a wonderful evening. Thank you again very much for all your details. By the way, I've just got another question. I'll just add this one. Tom JXQD says, any results from using LITS multi-strand wire?
LITS wire. Well, you would not use LITS in a transmitting capability, possibly for QRP, but the wire strands are so small. Number 40, for example, they're like hair. They'll overheat and burn up. Now for receive, that might be just fine, but this particular transformer is not as sensitive to interturn capacitance as some of the old transformers and coils that had many turns, and you needed to minimize the parasitic capacitance in the coil, and so you would use Litz wire. But that's not really a big concern with this particular design at HF.
Right, brilliant. Okay, well, I hope that's helped you, Tom, and hope it's helped everybody who's asked a question tonight and everybody who's been watching this. Really, as I said, what an excellent talk about a very popular antenna in this club and probably many others as well. And thank you so much for explaining in great detail how it works and how you can make the most of it. Thanks ever so much for joining us again, Maud.
Glad to do it, and we'll see you next time.
Look forward to it. Thanks very much. Bye-bye.
73.
7-3. There we are. That's Ward, N0AX. What a really good in-depth talk about that. And as I said, to be honest, we don't always get people this many watching as well. I was over 50 at one point and live, and we don't usually get people, to be honest, staying as well. So it's really good. Obviously gripped a lot of you there. So thanks again to Ward for an excellent talk tonight. That's about it for this NARC Live. As I mentioned earlier, we will be back again next week. So next Wednesday. So Sunday at 7 p.m. the GB 2RS News on GB3MB. Then next Wednesday, as I said, July the 13th, we're back here again for a double week, a second week of NARC Live. And we've got Bill W5SJ talking about being an accidental contester. We'll be back at CNS School on 2 weeks tonight on August the 20th. So before then, please do keep us up to date. Send us your picture or bit of fun, or what you've been doing in the summer weather with your radios or anything else really. Do send them to the usual address. We look forward to hearing from you. But that is it for tonight. We look forward to seeing you next Wednesday. Until then, from Tammy M0TC, the laugher, the giggler herself.
Bye-bye.
And from me, David G7RP. Take care of yourselves. Look after each other. Good night.